The most important force in the universe is energy. It lights our homes, charges our phones, grows our food, and keeps modern life running. But the way we make it is still flawed. Burning fossil fuels fills the sky with pollution and heats the planet. Splitting atoms creates dangerous nuclear waste that can last thousands of years. And depending only on solar panels or wind turbines mean we lose power when the sun sets or the air is still. It's a strange irony. Above us burns a perfect source of clean, limitless energy, the sun. Every star you see in the night sky runs on that same simple reaction. So what if we could recreate that process here on Earth? What if we could build a miniature star, one that never runs out of fuel and never destroys the planet? For decades, it sounded like science fiction, but recent breakthroughs have changed everything. The question is no longer if we can do it, but how soon. And if we succeed, the world will never be the same. The process that powers the sun and stars is called nuclear fusion. In simple terms, fusion means taking two tiny atoms and forcing them to combine into one. When that happens, a small amount of their mass turns directly into energy. Following Einstein's famous equation, E equals mc squared. That's why fusion releases so much power. But there's a problem. Atoms don't like to be pushed together. Their centers, called nuclei, are both positively charged, which means they naturally repel each other, like trying to force the same ends of two magnets to touch. To make them fuse, you have to smash them together so fast that they overcome that repulsion. That kind of speed only happens when the atoms are heated to more than 100 million degrees Celsius, hotter than the core of the sun. At these temperatures, atoms lose their electrons and turn into a glowing, super hot soup of charged particles called plasma. Stars achieve this easily because their enormous gravity squeezes their cores tight enough to keep the reaction going. On Earth, we don't have that gravity, so scientists have to find other ways to trap and control the plasma long enough for fusion to occur. Why go through all this effort? Because the reward is unbelievable. 2 pounds of fusion fuel could produce as much as 55,000 barrels of oil. A single glass of seawater, rich in the hydrogen isotope deuterium, could power your home for years. The fuel is nearly limitless, and it produces no greenhouse gases. So how do we actually build a star on Earth? Scientists use two main methods: magnetic confinement and inertial confinement. In magnetic confinement, huge magnets trap plasma, an extremely hot gas made of charged particles, inside a donut-shaped chamber called a tokamak. The plasma never touches the walls because even the slightest contact would cool it instantly. The biggest project using this design is ITER in France, a $20 billion experiment to see if fusion can run non-stop. Inertial confinement works differently. Instead of magnets, it uses short, powerful bursts of energy. At the National Ignition Facility in the US, 192 lasers all fire at once at a tiny fuel pellet. The blast squeezes it so tightly that the atoms inside fuse together, releasing energy. In December of 2022, scientists at NIF reached a major milestone called ignition, the moment when the reaction gave off more energy than was put directly into the fuel. But there's a catch. While the fuel released about 3 units of energy for every 2 units it absorbed, the lasers used around 300 units of electricity to make it happen. It's like using a blowtorch to light a match. Still, that success proved that physics works. It's no longer a question of if fusion can happen, but how efficiently we could make it happen. Engineers are now racing to shrink these massive systems, build faster and cheaper lasers, and design reactors that can repeat the process continuously instead of once per day. Now, the fuel itself comes from 2 types of hydrogen: deuterium, found in seawater, and tritium, which is radioactive and very rare. There's only about 20 kilograms of it in the world. Future reactors will need to make their own tritium using a lithium blanket, where neutrons from the reaction hit lithium and create new fuel. It's a clever system, fusion creating the fuel to keep itself going, but building it at scale is still one of the hardest engineering challenges on Earth. If fusion is so hard, why not just use regular nuclear energy? The difference is safety. Traditional nuclear power, called fission, works by splitting heavy atoms like uranium. That process can create dangerous chain reactions and radioactive waste that lasts for thousands of years. Fusion is the opposite. It combines light atoms like hydrogen instead of splitting them apart. If something goes wrong, the reaction instantly stops. There's no meltdown risk, no explosion, and it can only happen in a controlled environment. A vacuum chamber hotter than the sun but surrounded by cold metal walls. It also produces almost no long-term radioactive waste and no carbon emissions. Fusion is clean, safe, and powerful. The challenge isn't danger, it's just making it work long enough to power the world. Fusion isn't ready yet, Most scientists agree that talk of commercial fusion within the next decade is optimistic. The first real power plants might appear in the 2040s, with global use coming later. Some argue that the billions spent on fusion should go toward improving solar, wind, or advanced nuclear energy. But the scientists behind fusion see it as an investment in humanity's future. The hardest problems, like containing plasma hotter than the sun, are finally being solved. What remains is not physics, but patience, the willingness to keep building, funding, and believing. The question isn't if fusion will happen, it's when, and whether we'll stay committed long enough to see it through. Every generation has its frontier. Ours might be learning how to harness the fire of the stars to power the world. If you enjoyed this video, make sure to subscribe to Forever Green for more stories about science, our planet, and the future we're building together.